This will be Professor Cohn's kind of last complete lecture, although on the last day of classes, the plan is we're going to take some of the time just to talk over what we've done and review things. And it will be really oriented towards general aspects of systems engineering. And Aaron, I'll turn it over to you.
Thank you. Today I'm going to lecture primarily on systems engineering, but management as it relates to systems engineering. I have several checks and balances in the course today. I got people from the Draper Laboratories and people from the predecessor to Draper Laboratories, MIT Instrumentation Laboratory, are going to check me to see if I say the right thing. First of all, I'd like to say to you as a class, I read your last submission of your reports, and I really thought they were outstanding. They showed a great deal of interest, a great deal of understanding, and a great deal of initiative, and so I really compliment you, and I'm sure your final reports will be better, but they really were very, very, very good. You've heard a lot of people talk previously, starting with, in my way of thinking, Dale Myers, who was sort of the person that started the program in Washington at the time. You didn't hear from another very important man, George Miller, who was really Dale's boss at the time. But George is still alive, still doing very well. And you didn't hear from a lot of other people. You did hear from Chris Kraft, which sort of set the tone, you might say, for a very interesting understanding of a man who really knows what he's doing and says what he thinks. But there are several other people that I'd like to talk about that had a great bearing on my career in terms of systems engineering. There were two people, both have passed away. One is Joe Shea, and Joe was a very remarkable engineer. He was a program manager of the Apollo program at the Johnson Space Center, then left and became vice president of Raytheon here, and then became a professor at MIT in the Aeroastro department. And I thought he maybe taught the forerunner to this course. He taught systems engineering. And Joe Shea was actually the best systems engineer I've ever met. So I'm going to talk a little bit, give you some understanding of my interaction with Joe. The best job I ever had, you might say, really, is I've had a lot of different jobs, but my first job was really working with the MIT Instrumentation Laboratory, where I met a great number of people. I'm not going to mention everybody because it would fill up the time, but had not been for the MIT Instrumentation Laboratory, they taught me systems engineering, but they also, it hadn't been for the MIT Instrumentation Lab, we wouldn't have gone to the moon on the schedule we went on. They really did a fantastic job, all these people. I mean, they were just, you might say, giants. There are great people at Rockwell and North American Aviation, such as George Jeffs, and great people at Grumman, such as Joe Gavin, and other places, but I have to say that the MIT Instrumentation Lab really was really carried the ball on understanding how to do guidance, navigation, and control. If you read some of the comments by George Lowe, who's the other person I'm going to talk about, and George Lowe is another giant, he says the most complicated system on the Apollo spacecraft was a guidance navigation system, if you read what he said. And that really was, you know, could you really hit a target 240,000 miles away and bring it back? But let me get back to Joe Shea. I said he was a great systems engineer, and Joe Shea taught me a couple of things. One, he taught me not to be afraid to make a decision. He said the fact that you are in charge, the fact that you have looked at all the information, the fact that you know the details, you're the best one to make a decision. And if your batting average can be, if you can make a timely decision, and your batting average is a little over 60%, you're doing very well. But the fact that you made it timely, and the fact that you understand it, you can make a change. You can change if you're wrong. And that always stuck with me, that not to be afraid to make a decision, because many times as you go through your role in engineering, systems engineering engineer, you're not going to have all the information to make a decision on a timely basis. It's just not going to be there, especially if you do a program that pertains to advanced technology, advanced research and development. That's the other thing. That's one thing that's very important. The other thing that Joe Shea brought to the table, we had, during the Apollo program, before we had Joe Shea, we would sit around a conference table in the early 60s trying to figure out what systems engineering was. We really knew it was there, but we couldn't really explain what we had to do. We didn't know what we really had to do. Well, when Joe Shea came, he brought with him the insight of what you needed to do systems engineering. Now, this is the Apollo stack, as you see it on the pad, you might say. The launch vehicles, the launch vehicle, the first stage, second stage. Then you get to the lunar module, the command and service module, launch escape tower. So that's what it looks like on the pad. Well, Joe Shea gave me probably the toughest job and one of the most important jobs I had in my career. He said, Aaron, you're going to be in charge of resolving all the ICDs, the interface control documents. That's all the interfaces between all the stages, between the command and service module and the lunar module, between the command and service module, lunar module, and the stack, between the command and service module, lunar module, and the launch complex. There's about 1,000 ICDs involved in that. And that was a formidable task because an ICD, interface control document, you can't design without the interfaces being defined, and you can't define the interfaces without the design. So it's really a chicken and the egg type thing. And it turns out that was a turning point in my career because we did do that. In fact, a little sidelight, a little interesting story. He anointed me to do this job, but he didn't just leave me there. He took me to the contractors. He took me to Draper. He took our MIT Instrumentation Lab. He took me to Rockwell. He took me to Grumman. And he took me to the Marshall Space Flight Center and Kennedy Space Center. And the funny part about it, he took me in to see von Braun, which, I didn't know about. I didn't know von Braun. And he said, Werner, this is Aaron Cohen, and he's going to resolve, we were in his big office at Marshall. He says, he's going to resolve all the ICDs, all the interface control documents. And Werner von says, that's wonderful. What's an ICD? So I knew I had a problem there right away, that here the man had charge of Marshall didn't know what an ICD was. But that was a little bit of a sidelight on it. I did have the job to actually resolve all the interface control documents. And that turned out to be one of my most interesting, most challenging jobs as a young engineer. It really taught me systems engineering because one of the important parts of systems engineering is understanding where the interfaces are and how you get the interfaces resolved. And you can imagine trying to get Grumman at that time and North American Aviation and Draper Labs or MIT Instrumentation Lab to agree on an interface document. I mean, it wasn't the easiest thing in the world to do, but we had, yes. Did you have a question?
Yeah, I'm just wondering, aside from
Sure, please ask questions.
Technically making sure that the interfaces are working and everything, what's involved in resolving an ICD?
Well, first of all, and that's a good question. First of all, let's talk, and I'm going to talk a little bit more about ICDs in general. ICDs you can define in several categories. One is mechanical or physical ICDs, bolt hole patterns, just how things bolt together. The other, you might say, is electrical ICDs. What kind of electrical signals are sent, and our electrical interfaces. And the other are functional ICDs. One of the big ICDs we had to resolve was a term called guidance reference release. When the Marshall had an inertial measurement unit in their instrument unit, and we had to have that synchronized with our system, or with the system in the command and service module. So what is involved in it is you sit down and you talk. You have a draft ICD, and we had these big meetings. We had them at the Kennedy Space Center. I don't know if you've ever been to the Kennedy Space Center, but we actually filled the firing room with people, and each group had a certain set of ICDs, a draft ICD, and they would sit down in working groups and decide what had to be done to get the interface compatible in terms of the three phases: mechanical or functional, mechanical, physical, electrical, and functional. and you just work out the details.
Aaron, we probably, you know, now in the 21st century, we ought to add data ICDs.
Data ICs, yeah.
Yeah.
Well, I think things have changed probably a lot since I've been involved in it.
I mean, remember Mars Polar Lander? We had English units coming
that's
over,
right, that's
and the people thought they were getting metric units. So, you know,
Well,
the data ICDs are also
you know,
critical.
and a lot of things are very simple and mundane. I can tell you a story with the crew. When we said you're going to have in-flight maintenance with the crew, and we gave the crew to change out a component, but instead of taking the screw out very easily, we had actually put Loctite in the screw, so the screw couldn't undo the screws. So there are very simple interfaces that have to be resolved. Some are mundane, some are very sophisticated. I don't know if that answers your question. The problem is there's no F equal MA, there's no closed form solution that tells you exactly how to do it. You just have to sit down and work it because the design hasn't been complete, and but you just you have ideas, you float ideas, you negotiate, you arbitrate, and then you come up with a decision. Main thing, you got to make a decision though, and somebody has to be there to make a decision. That was my job, to make a decision. So that was what Joe Shea left me with, and people that know him. Will agree that he was an outstanding engineer, but also probably one of the best systems engineers we ever. Larry, do you know what course Joe taught when he was here?
This one.
He taught this course?
Yes.
I thought he taught this course because I remember I came up and gave a lecture for him, and I think he was.
Until he was taken ill.
Okay. Let me talk about another person that was very prominent in forming my career. His name was George Lowe. George became, after Joe retired, George Lowe became the Apollo program manager at the Johnson Space Center. George was very much a disciplinarian. He always had time to see you. But there's several criteria in seeing you. You had to tell him what your subject was, or say how long you wanted, and why you wanted to see him. So when you met with him, if you asked for 15 minutes, you had 15 minutes. And no matter how important the job was, if you didn't finish what you had to say in 15 minutes, you were out the door. And you only did that once. But you didn't ask for too much time either, because you got penalized if you said you needed an hour and you only took 30 minutes. So he was very much a disciplinarian. He actually, after he retired from NASA, after he retired from the Apollo program, he became deputy administrator at NASA and was very instrumental in the shuttle program, and then retired and became president of Rensselaer Polytechnic Institute. So George had a very illustrious career. He passed away several years ago. One incident that might be of interest to you, and I recall it very vividly, I don't know if everybody else does, but we were getting ready to go to the moon on Apollo 11, and as you do, this is on Apollo, and you monitor all the systems very carefully. And we were monitoring the inertial measurement unit in the lunar module, which is right here. And for some reason or other, the drift rate changed fairly drastically. Now, it was still in spec. The drift rate was still in spec, but it changed. And to get to the lunar module and change out an inertial measurement unit on the pad is pretty hard to do. First of all, the lunar module has very little structure to it. It's made out of Reynolds wrap, really. I mean, it doesn't have very little structure to it. And so we reviewed it with all the people involved, reviewed the data, and concluded we concluded very clearly that there was nothing wrong with it. And so we went to George Lowe, and we told him the story, a unified story. You know, the MIT people, the Draper Lab, the MIT Instrumentation people, the Rockwell people, everybody, JSC people. And George Lowe listened very attentively, and then said, "Can you explain why it changed?" And we said, "No, we're going to change it out." So that's the thing that always stuck in my mind. If there's something that you don't understand, then you need to take some action to fix it. And to me, to me, that was a very important part of my learning process. And so those were the people, you might say, that really had an effect on my systems engineering thought process. The other thing I want to talk about with you today is you heard a lot of people talk that I would class as subsystem managers. There were subsystem managers. You heard Tom Moser talk about structures. I don't know if I can recall them all. Al Levere talk about the mechanical systems. You heard about Bob Reed talk about aerothermodynamics, Bas Red by aerodynamics, Henry Pohl about reaction control systems, auxiliary power units, and hydraulics. Walt Guy about environmental control system. You heard these people. These people are what I call subsystem managers that actually, in some regards, worked for me, and in some regards didn't work for me. And that's what you call a matrix management system. Now I'm going to talk about matrix management. Matrix management was actually a very popular management system several years ago. I don't know if it's used today or not, but matrix management is a type of management basically used by large organizations, and primarily because what it is, it's large projects are organized with teams that work on a functional rather than a project basis. In other words, these people I just talked about actually had two bosses. They had a boss in their engineering organization, a very famous man named Max Faget, and then they had another boss, which wasn't so famous, was me, and I was their boss that controlled the project's cost, schedule, and performance. And they actually reported to me on that, but they actually had two bosses. And so you do that for several reasons. You do that in order to conserve resources, and many large companies do that. The other way of doing it, would be to put all that engineering talent in the project office. And you can see the advantages and disadvantages. I'll show you more explicitly the advantages and disadvantages on that. The advantages are that you have a dedicated organization. The disadvantages are that when the project's over, there's no place for these people to go. And I don't know what you use at, you have a matrix at the Draper Labs today? Do most companies, I'm not that close to industry. Do most companies use matrix today? Or?
Yes, most aerospace companies
use matrix. I don't.
Too many projects that change all the time, and you have to do somebody has to be responsible for the people.
See, now that's an interesting part. We at the Johnson Space Center didn't have that many projects. We only had really maybe one or two projects, but we still use matrix management because there is a check and balance on matrix management which you don't get on centralized or project management. So there is advantage to it. There are some disadvantages to it.
The instrumentation lab was project oriented.
The instrumentation lab was project oriented at the time?
When we did Apollo.
You were project oriented? Because you had one project and you were just project oriented.
They were all NASA projects.
See? So there is their advantage in this. I don't know what, I think I had some dealings with Ford Motor Company, and I think Ford Motor Company actually uses matrix management. I think most large companies use matrix management today, I guess. Anyway, so that's really the advantages and disadvantages of matrix management. And a lot of these things I've already said. Under matrix management, all the people who do one type of work are in a pool. For example, all the engineers be in one engineering department and report to an engineering manager. That's what I said. They all report to an engineering manager. In this case, the name was Max Faget. And if you do history in the space program, Max Faget becomes a very prominent name. He was really the, you might say, the original designer of the Mercury, Gemini, and a lot to the Apollo spacecraft configuration. So you'll run into his name time and time again. But he's the guy, and the interesting part about it is that Max and I used to go at it tooth and nail. I mean, his people would want to do something, like Walt Guy, and Walt's was at that time a very stubborn guy, person, and he would want to do something, and I wouldn't want to do it. Well, he would go to Max, and then Max and I and Walt would have a meeting at the summit with Chris Kraft, because Chris Kraft was both our, so it was a common point. We all went to see Chris Kraft. Sometimes I won, and sometimes I lost. But I learned actually to love it. even though it frustrated me, I learned to love it because there was that check and balance on me that I could not do something that was going to actually be wrong. Somebody else was going to catch me if I did something wrong. Now, I honestly do not know today what the NASA uses, whether they use matrix management on the shuttle program or on the space station program, or how they're going to do it. Do you have any idea?
The shuttle was certainly much more project-oriented. We don't have the same, I mean, there is an engineering division at JSC,
Yeah.
but during the shuttle,
It started out matrix
Yeah.
management,
I think it really decreased, and there was no more Max Faget
Right.
running things in that same way.
and so that is a very, in my mind, at least in my way of thinking, that is probably one reason why problems occur, because you don't have that independent check and balance. So there's a very good reason why matrix management, I think, is important, even though you don't have a number of projects that would cause you to do matrix management. Well, it says these same engineers may be assigned to different projects and report to a project manager while working on that project. Therefore, each engineer may have to work under several managers to get his or her job done. That's what I was saying. It just turns out that you do have that type of problem in doing that. Proponents suggest there are two advantages to matrix management. First, it allows team members to share information more readily across task boundaries. Second, it allows for specialization that can increase the depth of knowledge. So you can see how, if you have a matrix manager, you can call on more resources to go to your home organization, facilities in terms of testing. I have worked under, when I was in industry, worked under total project organizations, and it has a lot of advantages and disadvantages also. The disadvantage of matrix management is that that employees can be confused due to conflicting loyalties. I mean, was Walt Guy loyal to Max Faget, or was he loyal to Aaron Cohen? Now, Max actually gave him his raises, but I had huh? Well, that's right, but I control the dollars for the project. But you're right, that's what counts. But they call that pink ticketed. He was actually pink ticketed to Max and actually worked for me, and I had to use all my persuasion to get him to do the type of job. A properly managed cooperative environment, however, can neutralize these disadvantages, and I guess that says that I had to.
Your organization was one program.
Excuse me?
In Apollo, there was one program.
Right.
But in Draper, for example, when we had these departments that were projectized, for example, we had Air Force, Navy,
Right,
and NASA.
yeah.
And we were doing accuracy evaluation for each one, and we developing the whole software from scratch for each one. It was different language, different computers, and you could compare results.
Right.
And when you have one engineering organization that does the same, at least
You
they can compare,
yeah.
and you have the
Yeah.
check and balance.
Right. That's very good. That's a very good point. Yes, Jerry.
There's a disadvantage, though. When we were a project organization, you had your thumb on the people who had to produce. In the matrix organization, oft-times, the engineering manager will shuffle his man right out from under you to another project.
That's right, and that's what I had to contend with. On the other hand, my strong personality and my goodwill kept it from going that way. And there was a certain amount of esprit de corps that they wanted to get the job done. So, it turns out.
At the end, it's the people.
It's the people.
Doesn't matter what organization.
That's right.
If the people are wrong, no organization.
Well,
will
that's
win.
absolutely right.
So you have to have the right.
Well,
people.
and that's why I brought some of these people to talk to these students, because these people were the people I worked with. Even though we argued at times, there's nobody that argued more than Henry Pohl and I did, but he's usually always right. But you can learn to live with it. Matrix management can put some difficulty on the project managers because they must work closely with other managers and workers in order to complete the project. The functional managers may have different goals and objectives. So I'm saying this as I present these charts, but I think you can you can visualize that. And don't hesitate to ask questions, because you got a lot of people here in the room today that can help answer some of these questions. Yes.
The point about check and balance, you have several managers. So
Yeah.
from my understanding, you have maybe a functional manager, then you have.
Well, let me tell you what I mean by check and balance. Let's say, and specifically, let me give you a specific example. Let's say Henry Pohl on the reaction control system wanted to do more testing, or wanted to do more stability testing. And I looked at my budget, and I looked at where we stood in the schedule, and I said, we just can't afford to do that. You know, we're just not going to do that. I made an arbitrary decision. Well, Henry would be very upset about that, and he would go to Max, his functional manager. And Max would say, boy, you're right, Aaron's crazy. So he would then call a meeting with Chris Kraft between Henry, Max, and myself to decide what we were going to do. And then Chris was the final word, the man you met. You know, he's a pretty strong guy. And if he agreed with Max, if Max had a convincing story, he would turn me around. And then we'd do the testing. And I just had to find the money someplace. But if I could convince Chris that Max was overdoing it, then I'd win. And normally I lost, but that's okay.
Do the engineers in any of these organizations that have matrix management feel that they have too many managers?
Well, it was frustrating to them a little bit. Yes, they did. It's frustrating because they had to feel that they were working for two different people, and it is a little bit confusing to them. I mean, they had two loyalties. As I pointed out, they had two. They essentially had two different loyalties. One to their functional manager, who paid their salaries, and the other to me, who really had the project. I had the money for the project and the schedule. So yes, it's a very tough thing to do. But as you can tell by talking to these people that experienced it both in Apollo and in the early days of Shuttle, they were very satisfied with the results. That's why it's very frustrating to some of us to see the way things are going, because we carried over most of these people you talked to, as are here in the room today, worked on Apollo, and then went and worked on Shuttle. We did the same process. We had the same Joe Shea, George Low process that we did. Yes. Oh, I'm sorry. Yes.
I think there is another disadvantage of project of matrix management, besides the fact that it's really interesting for a very large project at Johnson Space Center. I think it can also increase the number of quite useless meetings, since you can always have disagreements between functional and project managers.
Well, that's absolutely true. Your decision-making process in matrix management turns out to be a little bit more cumbersome, and then if you have direct control. In other words, you have your thumb under everybody, you can get a decision pretty quickly. On the other hand, you can violate some good checks and balances. So you give up the process of a rapid decision-making process versus having some good checks and balances. Is that it? So your thought's very clear. Okay, I'm going to leave that subject unless there's any other questions on it.
Can I just bring up something?
Sure.
I'd welcome your opinion on this, Ellie. And there has been a big change in NASA recently, which is affecting management, and that's because NASA has gone over to what they call full cost accounting, which means that during all of this time that the engineering organization
That's true.
maintained their engineers, they paid the salary, and then they would be assigned to projects as required. The system as it's now working it's supposed to be much more like in industry, where the time of every engineer has to be billed to a specific project, and if you don't have a project to bill your time to, ultimately you become redundant. And so you may have, those of you who read Aviation Week and Space News, I hope all of you do, are aware that NASA is doing a lot of downsizing. It puts a lot of constraint on management. Now, in industry, obviously people have to be paid for, but it is, I mean, how do are there always enough projects to bill people to? I mean, or
there is never a situation that you have the exact number of people. You either short of many people, which is now the situation in Draper, or you don't have enough money. So what you do in a place like Draper, we have our own money that's called internal research, and we use some money of that as a flywheel, and we keep those people that. But those has to be people that the company believes that they can be used in the future. There's no point in keeping people that nobody wants. And actually, the matrix system, and I talked about it with Jerry because we are doing the evaluation, that's why I had to leave, is really sorting the people out, because when it was a big project, it was a big family. The guy owned them, he knows them, and
That's true,
now
That's true,
you work at the function organization, and we send you to work for the program. He wants the best people for his
Yeah,
project.
that's
He
right.
will say, well, I don't want this guy. Now, if it's a mediocre guy, we'll say, look, you can't have the best. You have to. But if it's somebody who is very weak, we'll say for one time, okay, maybe he didn't get along with the program manager, so put him in another program. But if we get the feedback, it doesn't work there, we know there is a problem. So in that way, we weeded out a lot of people that, if you have the old system, probably will stay and make us less efficient.
okay. Well, I hope
So NASA will be more efficient now.
I think that's true. On the other hand, it causes a lot of pain and yeah.
Very difficult to
Yeah.
let people go. But that's part of management. It's not just going
right.
to parties; it's make
That's
the
right.
tough decisions.
That's right.
Okay.
Yes, there's a question.
I guess another angle on the very tough to let people go, it's I've noticed that it's extremely difficult from a bureaucratic standpoint to let somebody go in government, and I'm just wondering, full cost accounting, okay, you decide it's time for this person to go, but there's just a lot of politics and bureaucracy and paperwork to go through to get somebody out of the organization.
There's civil service laws which have to be complied with. It is difficult, and I mean, I have to say, I agree with Ellie that in the long run, I think NASA will become more efficient.
Well, to answer your question, there are several ways to let people go. One is if they really have done something bad, you have a board and you go through it and you release them. The other is if you have, if NASA has a downsizing, which is called a RIF, reduce in force, then you can arbitrarily let people go. I didn't mean to interrupt you, Jeff. But those were two ways to let people. I do think, though.
I'll just add there. Yeah. The third way, which NASA is also doing, is you can offer what they call buyouts. So they offer up to $25,000 if you'll take early retirement. So a lot of people do that.
And companies, not government, have a much easier time. I don't know how Draper is, but the companies have a much easier time letting people go than other places. But management, that's about all I was going to say on management. Now I'm going to get into the, you might say, the interesting land of systems engineering and talk about systems engineering a little bit. My charts are sort of yellow because they go way back. It turns out systems engineering has been studied a long time, a lot. And there are many aspects of systems engineering that some people in the room may or may not agree with. I've had time to reflect a little bit from my days at NASA in both Apollo and Shuttle and in Space Station. And I was, as I say, director of the Johnson Space Center. I was deputy administrator, acting deputy administrator under Golden for a year. And then I taught at A&M. And all that time I've had time to reflect. And I've had time to do some, you might say, some research of what I thought systems engineering was and how you explain it. Well, I'm going to try to do that today. People in the room may or may not agree with it, but it's my thought process. And it turns out that much of this information was gathered from studies done by the military. Mil-specs on systems engineering. They've spent an awful lot of money studying systems engineering. And many of these charts are plagiarized, you might say, from those studies. And they look sort of like they're yellow, and they are. But let's start off systems engineering heritage. You know, systems engineering, as we pointed out, is not new. You know, the pyramids, that was a real systems engineering problem. I don't know how they did it, but it was a real systems engineering problem. I don't know if even Jim Nevins could do that. That was a tough job. Broadcasting service and standards. Now, most of the time when you talk to people about systems engineering, they talk, in fact, I did a lot of research on that, they talk about systems engineering as operations research. Well, I don't think that could be further from the truth as systems engineering. I think it's a tool maybe used in systems engineering, but it's not really systems engineering. The RAND Corporation develops the systems analysis. The Bell Labs telephone systems, that's, of course, where Joe Shea came from. Joe Shea came from the Bell Labs at that time. NASA military systems, and these are MIL standards, and the Army, and then Systems Engineering Management Guide, Fort Belvoir Defense Systems Management College. So there were a lot of studies done for systems engineering. And we in Apollo were trying to do systems engineering in the 1960s for Apollos when we tried to start to do it. By the way, these charts are not on the web, but I'll give these to Jeff and they'll be on the web. And trends highlighting the need for increased systems engineering. There's a need to manage the total picture in the area of increasing system size and cost. But even a small project has systems engineering. If you can think of how you design a bicycle, how you design an automobile, I mean, these are very complex problems. They're not simple. They're really systems engineering problems. But the increasing technological growth and specialization, increasing systems complexity. You know, the PC is a fantastic systems engineering problem, and I guess Bill Gates saw the need for a true systems engineering job and made a lot of money on it in terms of what he did understanding systems engineering. Increasing sensitivity to environmental factors and increasing cost of life cycle. So all those things make the trend in systems engineering important. And as I look at your reports, I really think for wherever you got it, I think you have a pretty good knowledge of what systems engineering is. So I'm not sure this lecture is going to help you that much, because I think you do look at it from a systems engineering standpoint. By the way, my last topic is going to be cost analysis. I'm sure you're waiting to hear that, because cost analysis is very hard for you to come to grips with. And I'm going to talk a little bit about how you would go about doing a cost analysis, which may not dot all the I's and cross all the T's for you, but I'm going to try to do that. So we're going to take a break about at 11, and then I'll have some time to go through cost analysis. Well, what is systems engineering? I don't know, you may not agree with this, but systems engineering is the application of scientific and engineering to transform an operational need into a description of system performance parameters and a system's configuration through an iterative process. Now, let me give you a need statement. When President Kennedy said we're going to send men to the moon and return them safely within a decade, that's a perfect need statement. Doesn't tell you how to do it. He didn't put a cost constraint on it. He did put a time constraint on it. And he told you what you had to do, but he didn't tell you anything about how to do it. That's a good need statement. That is a very good need statement. I don't know if he knew if he did that for that reason, but he gave the public and NASA a very good need statement. Now, our job was to transform an operational need into a description of system performance parameters and system configuration through an iterative process. And that's an exercise left to the student. That's not easy to do, but that's really what you need to do. Now, to integrate technical parameters and ensure compatibility of all interfaces, that's what I talked about. You talked about physical, functional, and program interfaces. They call them different things, but basically interfaces become a very important part of the systems engineering process. And the other factors into the total engineering efforts meet cost, schedule, and technical performance. What is that? I think Professor Hoffman talked about. That's the three-legged stool. It's schedule, performance, and cost. It's a continued trade-off because you're going to have a criteria of, whereas President Kennedy didn't give us a cost, he did give us a schedule and to a certain extent performance, but he didn't give us a cost. Now, as it turns out, cost always becomes a factor. It always becomes a factor. But those were the things that really comprise, you might say, in simple-minded terms, systems engineering. I can't emphasize those enough to say that. Now, I don't know if that's how you visualize systems engineering or how everybody in the room visualizes systems engineering, but that in the design process is really what systems engineering and design is all about. Now, whether we utilize that always in design of our projects, I can't say. I think we could have done a better upfront job in systems engineering on the shuttle. I really think we could have. I see things we could have done differently on the shuttle today and if we really practice a true systems engineering process. It's very difficult to do because you can stay in this systems engineering loop a long time and not get anything done. You know, there's an old adage, you know, if you never get out of this loop, you can do something, and never get anything done. So you got to be very careful with that. What is the role of systems engineering? Technical customer interface, requirements definition. Requirements definitions sound very, very simple, but requirements definition is probably one of the hardest things you have to do, is to find out what the true requirements are. And unfortunately, requirements do change as a function of time as you go through the phase of the program. But requirements definition is very, very difficult to do and very, very important to come to grips with. As J.R. Thompson talked to you, I don't know if you recall J.R. Review of the service module the shuttle main engine, SSME. He said had they widened the throat a little bit, they would have reduced the complexity of the design and development of the main engine, made it much more reliable, but you would give up some performance. Now, why didn't we do that? Why didn't we do that? Because there was the requirements to advance technology. And I think JR made a very, very important part there, that those are things you need to look at early in the program. So requirements definition are very important, extremely important. And it's very difficult to get to the bottom of it. Requirements definition is a task in itself. And then, of course, there's requirements management, analysis and flow down, audit, and then again you get interface management. Risk management is becoming a big item today. If you listen to, you heard Bob Siemens talk, and I didn't mention Bob Siemens. He's another very, very important man in this whole era of Apollo and hand down the shuttle. Bob Siemens, his role cannot be stated too highly. He did a fantastic job. His risk management was very interesting. I heard him talk not too long ago, and he said that the risk management in terms of cost and in terms of human life for the Apollo program was accepted. Was accepted not only by the executive branch, the legislative branch, but the public. So risk management needs to be accepted, and that's one thing that is very, very important. Understand what the risk management is in terms of life, in terms of costs, and in terms of what it's going to do for you. So risk management is very important, and it's the function of the systems engineer to bring that to bear. Performance management, design process, so forth and so on. Technology need identifier. You know, I had the reputation of not wanting to advance technology, mainly because of budget constraints. I wanted to go with given technology. Is that right? I don't know if that's right or not. But the point being is that technology can drive a program. The fact that you have to develop the technology can drive the program. So these are what the role of a systems engineer needs to do to figure out how they're going to handle technology. they're going to advance technology or not. Now, what is a system? A system is a complete solution to a defined need in its full environment over the prescribed life. The system includes hardware, software, documentation, human resources, non-human resources, esoteric factors. So it includes almost everything you can think about. Software turns out to be a big driver today. Software in the system turns out to be one of the largest drivers. Some of you asked me, and I hope it helped, what was the cost of the shuttle guidance and navigation system? I don't know who asked me for that. Somebody asked me what was the Apollo. Was that helpful to you, that the number we gave you? The shuttle. They want to know the shuttle. Yeah. So, but the factor it didn't separate the cost of the software and the hardware, and the hardware came on pretty much on cost, but the software was a lot higher.
It was exponentially growing.
Yeah. Software turns out to be, I don't know, Jerry, you want to say a word on software? Is it?
The problems of software was the issues of validation, verifying, test, retest, and then every once in a while somebody would come along and say, well, but we really ought to add this.
Yeah.
And the adding on was a killer.
Well, as Bill Tyndall used to say, it's sort of the garbage dump for things you couldn't do in the hardware.
The number that I remember that at some point, when you wanted to change one line of code, IBM wanted $1 million at that time. One line of code, because they have to check the whole software.
Yeah.
So that's why they have the software control board, out in Aldridge. It sits there, said we can't do it.
That's right. Yeah. I remember when I retired, Dave Leitsma, who was head of the astronaut office at the time, said that he thought he could get a change through Aaron Cohen. I forgot, it was something to do with return to the launch site. I don't remember what it was, but it was some kind of program he wanted to put in. So he talked to everybody, and they all approved it, and it came to me, and I turned it down. And he said, at my retirement party, he said, now Aaron's leaving, maybe we can get it approved. But software changes do increase the cost of the program. Simple system example: Space Shuttle, your house, electronic calculator, freeway, Golden Gate Bridge, barrier, rapid transit, computers. A system really involves everything. Almost everything you can think of is a system. The other thing that's interesting is this chart right here. You may have seen this chart before. You've seen it different ways. But the importance of systems engineering. The systems engineering is doing the right thing right. As systems increase in complexity and value, early systems decisions become increasingly important. It shows that actually in the impact of program funding, when 10% of the program funding is accomplished, you've actually committed 90% of your dollars. Systems engineering decisions have actually committed 90% of your dollars. So that means early decision making on systems engineering, whether you're going to make the engine throw it wide or not, actually impacts the program very heavily earlier. So that's why systems engineering is so important. Systems engineering is requirements and solution management. Understanding, analysis, allocation, so forth and so on, which really affect performance, cost, and schedule. And there's the three-legged stool again. So this really says that if you remember certain parameters, the continued cost trade-off between cost, schedule, and performance is really one of the most important things you can understand. And that is really a systems engineering job. One thing I'd like to talk about is the attributes of a systems engineer. Systems engineers are very hard to come by. They really are very hard to come by, and it's almost hard to tell you how to become one. There are courses you can take, but one thing I would suggest you do if you really want to be a systems engineer is you specialize in one technical area, whether it be structures, whether it be thermodynamics, heat transfer, guidance and control systems. Specialize in one area. That's the first step. So you need to be competent and show your competency in one area. But then you need to be then you need to broaden out a little bit and look at how people actually operate. Good judgment of technical competence in others. Ability to build trust of team customer management. And that's what this course is about, to work as a team and to have relationships with each other. I don't know if it was true at MIT, but in many years ago in universities, it was very bad to work as a team because you tended to rely on each other. And they wanted to have independent research, independent development. So students were not really encouraged to work at teams. I don't know if that's true at MIT, but it was certainly true at some other universities I know. I don't know, was it true?
We've gone through a major shift, and I think the rest of the country is as well, from individual to team effort.
Yeah, team effort.
Particularly in engineering.
That's right. I know we had at A&M. When I went to A&M, first one, well, they thought it was terrible. You know, some of the professors thought it was terrible working as teams. But
the difficulty that all the top universities have is you guys are all admitted on the basis of your high school or your college grades.
Yeah.
So those were individual efforts that got you here, and now we're saying, well, put the emphasis on team activity. The Japanese have traditionally done that far better than
That's
we
right.
have.
Just wanted to strengthen what you said, because a lot of people think that the system engineer should be a jack of all trades. He should know a little bit about everything. That's absolutely not true. You have to be very good at one specific
That's right.
area, and that's your baseline.
That's right.
That's how because the most difficult thing in engineering as a manager is to make decision when the guy who comes to you know about the subject more than you,
That's
because
right.
he's the expert. And the only way you can do it is by knowing how an expert behaves
That's
and
right.
does it in your
That's right.
area of expertise. You can make that judgment. So it's some people are confused on that, but I think that I 100% agree with you. You have to be an expert in one field, otherwise it won't work.
Yeah, I should say there have been a lot of discussions among the faculty in Aero-Astro department and perhaps in other departments as well as to when systems engineering should be taught. Should it be taught at the undergraduate level? And right now, the guiding philosophy in the Aero-Astro department is to devote undergraduate time really to building up expertise in the individual subject matter, as Ellie said, with the idea being that wait until you really have a good grounding as an engineer in one or more specific subjects, and then at the graduate level, that's time enough to actually look at systems engineering as a discipline so that you can draw on the expertise that you've built up. That's not a universally held decision, and there are people who make a good pedagogical case that you can actually start teaching principles of systems engineering right from the freshman level, and we try to, in the whole CDIO philosophy that our department tries to follow, we try to develop these principles which we think will then be useful as you get into more technical aspects of systems engineering level. So we always try to balance the technical expertise with the systems level thinking.
Yes, Jerry.
I'd like to point out that in organizing teams, the key important feature of that is to have that systems engineer who's organizing the team and setting up the meetings to know why and who should be attending. I attended a number of space station meetings where they had these product teams where every company in the world was there, and you had 50 people sitting around, and there were only 4 who were real contributors, and the others I could swear were falling asleep. So you fundamentally have to have good management in team setups.
Well, you're absolutely right. Of course, one of the problems with Space Station, in all honesty, if you had tried to devise a management system that was complex, the space station system would have won, because it's probably the most complex management system. In fact, I tried to explain it to Bob Gilruth one time, who was another man I should have mentioned. He was director of the Johnson Space Center, and he came to see me, and his eyes just rolled back of his head. He couldn't figure out what I was talking about. So you're right. But you know, the other person that agrees with you, Ellie, is Chris Kraft. Chris Kraft feels very strongly about becoming an expert in one field before you tackle something. Self-motivated, able to motivate others. You know, in matrix management, that becomes a good systems engineer if you're able to motivate others. Methodical, analytical, intuitive, questioning, open-minded. I think that's one of the key points, being open-minded. If you make a mistake, be ready to accept the mistake and correct it and make a change to it. That's very important in a systems engineering, especially if you have to make some important decisions. Confident, good communicator, and high level of integrity. So that is really some of my background on systems engineering. Now let's talk a little bit about more how you go about doing it. A system is generally considered a conglomeration of objects that perform a specific. Thank you, Ellie. See you. Thank you. Thank you. Thank you. It's considered a conglomeration of objects that perform a specific function. And you can think of those. I mean, you can think of all those in the laptop computers you have, many things like that, which we talked about. And I mentioned this before. This is what I say. It's a postulate, or whatever you want to call it. What is important for the whole system is nearly identical to what would be the best in the long run for each of its components. However, what is best for each individual constituent may not be the best for the whole system. And so that really is something you need to keep in mind. That's really the postulate of systems engineering. It may be the right thing for the system, but it may not be the right thing for the total configuration. And the systems engineering process is the customer user need analysis, mission requirements, functional analysis, system concept, development, trade-offs, design. Now this is systems engineering as it pertains to design. Now there's systems engineering as it pertains to operations, but this is systems engineering as it pertains to design. Design, optimization, requirements, flow down, technical communication, design assurance, verification, audit, and then you go through this iteration process. So I'm sure this is, in fact, this is what you do in your mind. I'm sure you do that. And when I taught this when I spoke about this to several of my professors, my friends at Texas A&M, they said, well, there's nothing in this. They said it's all common sense. And to a great extent, it is common sense. But the problem is, do you really practice it? Is really the problem. Do you really have a process in place, and do you really practice it? And we find that we don't really practice it too well. And we say this over and over again, but the three factors of systems engineering that will be the cost, schedule, and performance. And that's the famous three-legged stool that we talked about many times. But that really is the essence. And you as an engineer going to work, getting paid, that's what you're going to be paid for, getting a product out the door that essentially meets the cost, schedule, and performance. You look quizzical. Excuse me, go ahead. Oh, go ahead. Go ahead.
The statistic that you gave, that after 10% of the project funding has been used, 90% of the requirements defined, or do you think that functioning there might change today now that we have faster prototyping tools?
It could change, yes. This was done some time ago. Technology is changing. Rapid prototype is changing. CAD design. A lot of things are changing, so it might be not quite as dramatic, you might say. But it's still going to be there. It's still going to be there. A lot of your systems engineering decisions are going to affect your end product very early in the game. Cost.
Yeah, reason why that 90% gets locked in is because of the difficulty of making changes once you've got all the plans drawn. And so to the extent that, you know, CAD systems make it easier to change drawings and, you know, propagate changes throughout the system, you know, it may be that making certain changes are less expensive than they might have been, but you know,
as Jerry said about software.
Yeah, you start changing your software around. You know, you've got to do re-verification and so on. So it certainly, to the degree that modern techniques might make things more flexible, that number might get pushed down a little bit, but generally, once you've gone through preliminary design review, you have basically set the parameters of your project, and you know, things have a momentum, and it really does get hard to change. And of course, once you've gotten to the critical design review, you know, at that point you're starting to cut metal. And then, you know, once you've actually started to build something, then the price of changes goes up astronomically.
When we did the Apollo program, we started in '61. It was my guess that by '64, not too far into '64, I remember June of '64, we had the implementation meetings in Apollo. And by that time, all the hardware definition was in place.
That's right.
The program went on after that. And the only thing that kept growing or changing was software. But the basic hardware picture was pretty much, the nail was in 1964, 3 years into the program.
Well, as Jeff said, once you start cutting chips and start cutting hardware, it's pretty hard to make changes.
If I can clarify, what exactly is it that's being locked in? That
well, basically your requirements. Okay. You see, primarily your requirements. What your requirements are is the big driver for the, and then once your requirements are defined, then you can actually start your iterative process of design. Once you get your functional performance requirements defined, you then start your design iteration, and you start locking into things, and pretty quick you start cutting hardware and software.
Yeah, I mean, hopefully you've gotten a sense from all of the lectures on the subsystems of the shuttle, the degree to which they interact with one another.
That's right.
So, you know, imagine...
That's a good point.
Yeah, I mean, imagine if, you know, halfway down the road, there had been a major change to the thermal protection system, which had bumped the weight up by, say, 20%. You know, that would have... You know, imagine the ripples that would have affected, or if somebody had wanted to change the requirements for cross range, you know, after you had done the basic design of the system.
Let me give you a very real example on that. We had the wing basically designed, and you know that the landing gear comes up in the wing box. Well, we came to the conclusion that if you blew one tire on touchdown, you could blow all the tires. And so what they wanted to do is increase the number of tires that went into the wheel well. And what would that, and that was pretty late in the program. I mean, we already decided we decided from the systems engineering point of view, we were going to have the number of wheels we had and go up into the wheel well, retract. But then came along a study that showed, well, if you blew one tire, you're liable to lose the vehicle on touchdown. So they wanted to go put more tires into that wheel well. Well, can you imagine what that would do? That'd be redesigning the whole wing, and the wing was built. So we lived with that. We lived with that as some risk, but you didn't make the change to it. So that's the type of thing that gets into it. And I'm sure there are a number of items I could talk about that would cause that problem to occur.
Now, sometimes, you know, if you come up with a problem that really would be fatal, you've got to change it, and you know, it could be that if you know, one of the examples being the O-ring seal on the solid booster, you know, in retrospect, people have said we should have changed that at the beginning. Now, who knows if on the you know, if on one of the shuttle flights a tire had blown and we had
That's
lost
right.
the entire vehicle, there would have been an accident investigation board, and they would have gone back and said, yeah, we were flying with an untenable system,
Right.
and we should have made that change. And you know, that's where the engineer who has become a manager is really faced with a tough life or death, potentially life or death decision. And you know, there's always an element of risk, but if you try to take out all the elements of risks, you'll never fly.
Well, that's absolutely right.
So how do you make that judgment? And as I said, that's why they pay you such a big salary, right?
Well, the interesting part about that is when I became after the Challenger accident, my deputy became a very good friend of yours, Paul Weitz. Paul Weitz was an astronaut, a Navy fighter pilot, and our job was to get the shuttle flying again after the Challenger accident. And we found, I thought I brought it with me, we found this picture of a ship on a very ominous sea. And it said, a ship in the harbor is safe, but that's not what ships are built for. So you can make it so safe that you can never fly, or you can never fly across country, or you can never take a train. So you got to use some judgment. And of course that risk level today is not very well accepted. Point I was trying to make is that if during the Apollo program it was accepted, we knew we had to take risks. And let me talk about, tell me when you want to break, Jeff. You want to break now? Or
Probably a good time.
Okay, all right, okay. Take about a 5-minute break. Continue on. I want to get to cost, but I got a few more things to say about this. Let me talk about a process. This is the process that in fact, we had a contract with Ford Motor Company, and I showed this to Ford Motor Company of the design process I would go through, and they said, that's very interesting. We studied for a long time. This is exactly what we use. To understand the need, and the need was not the Ford Edsel. I mean, that was not a good need statement. But you need a need. You need a need analysis.
I don't know if any of the students in the class know.
Ford Edsel, that was.
Maybe.
Well, I tell you.
It shows up in crossword puzzles.
I'll tell you, you need to talk to Henry Pohl. Henry Pohl, who you heard lecture, still has an Edsel. Henry is probably one of the few people that still has an Edsel in his garage. But Henry has a lot of things like that. But Henry still has an Edsel, so you need to get Henry. But you need to do a need analysis, understand what the need means. You need a function structure. And actually, I saw in some of your reports, I saw very good examples of all these. Maybe not in all the reports, but I saw somebody talking about the needs, somebody talking about need analysis, somebody talking about function structure, requirements. The hardest thing for engineers to do, especially young engineers to do, is to make some assumptions and constraints and do some preliminary calculations. It's very difficult for them to do that. They like to see F equal MA. And I once mentioned that to Joe Shea, and he said, I'm glad you were still on your formula when I talked about F equal MA. You need some calculations, and then you need to do some conceptual designs. And that's really, you might say, the design process. And I think you can use various forms of it, but that's probably the best form of it you can think about. And systems engineering, interdisciplinary activities, customer need, functional identification requirements, an iterative design process with reviews at various stages, conceptual, preliminary, and final designs. And that's what Professor Hoffman was talking about. As you go downstream very quickly on that, it becomes harder and harder and harder to make changes. Let me now stop with systems engineering. Not that I couldn't go longer, but let me now stop with systems engineering and talk to you about a subject you're probably having more problems with than anything, and that's how you do a cost analysis. And unfortunately, I'm not going to give you a closed-form solution for it, but there is none. And not only that, my biggest, I did the 90-day study when President Bush, huh? Well, it was Bush.
Bush.
He stood on the steps of the Smithsonian, and Dick Truly appointed me to do it. And that study was really panned by everybody because they said, give us a cost analysis. And I really thought they wanted to know what it was going to cost. So I told them. Well, they didn't like it. I really, in all honesty, I wasn't really that high because it was a 30-year project, and I gave them the cost for a 30-year project, actually building vehicles, launch vehicles, technology. But nevertheless, I had my day in the barrel on cost analysis. So let me talk a little bit about cost estimation techniques. It turns out some of you are trying to use it. I mean, you're trying to find, here are the cost estimating techniques. Expert interview. You talk to an expert in the field, if you can find one. Parametric analysis. I'm going to spend most of my time talking about parametric cost analysis because I think that's the one that pertains to an engineering design course. Parametrics, because it's in terms that you understand weight, performance, that type of thing. I'm going to talk about that. Analogies. And then the engineering, which is really the you might say the grassroots or the build-up of what it's going to cost for engineering hours, manufacturing hours, and that type of thing, which is pretty hard to do. So I'm going to go through those. Now, some of you have tried to do some of these. Some of you have tried to call contractors to find out what a particular thing was going to cost. Some of you have tried to find out what the shuttle guidance and navigation system cost. So you're trying to do it. It's not easy to come by. You call a vendor, and he says, well, he'll quote you, but he wants to know what you're going to use it for. So it's hard to do. I know it's very, very hard to do. So you're going to buy, yeah. So I don't minimize the job you have in trying to do a cost estimate, but you got to recognize that that as an engineer and you go out and start to work, they're going to want to know what this thing is going to cost you and what it's going to cost, what outlays you have to make. Now, this is the cost estimating techniques over the project cycles. You can see as the project goes along, you have this so-called parametric methods, analogies, judgments, system-level CERs, cost estimate relationships. And that's a very key thing, cost estimate relationship. I'm going to talk more about that. But let me tell you what a cost estimate relationship in a very simple-minded approach is. Let's say you're going to go buy a house. What is the first thing you want to know about buying a house? How many square feet do you have, right? And you take how many square feet you're going to have, and you usually know about what it costs per square foot in the area you want to buy a house in. So you multiply that, and you get a rough estimate of the house. Now, there's another factor that goes into that. There is the culture. Where are you going to build this house? It's going to affect the cost per square foot. If you build it in a very expensive neighborhood, I always give the relationship in Houston, because I know Houston. If you're going to build it in Clear Lake, where NASA is, it's one culture. If you build it in River Oaks, where the very wealthy oil people live, it's another culture. So the cost per square foot in Clear Lake is much lower than the cost per square foot in Clear Lake. But you can get a rough estimate. But that's a very simple-minded CER. It's a cost estimate relationship. They become very, very complicated when you talk about past history, when you talk about weight of spacecraft and so forth and so on. I'll develop a little bit of that. General subsystem CRs and calibrated system CRs. But these are the parametric methods, and you can see how where they're used, and analogies and judgment, and they're used for a certain period of time. Then, when you get to the phase B or CD, you talk about component buildup estimates. I'm supposed to chart here. Detailed estimates and vendor quotes. So that's the sort of the schedule. And this was provided by the cost technology over the project cycles by the Lunar and Mars Exploration Office. That was the old lunar, I mean, it goes way back. It's been abolished and now restarted again. But so that's the cycle you go through. And of course, you're in really the phase A. So it's going to be pretty hard for you. It's going to be pretty hard for you to do the direct methods. Even though you may try, it's going to be pretty hard for you to do that. You almost have to use some type of parametrics. And I'm going to talk how you do a parametric. I'm going to talk to you how you do both of them. And this can get you into more trouble cost estimate gets you in a lot of trouble. How many in here are familiar with what we call a work breakdown structure? Okay, good. Well, a work breakdown structure is really the management tool that's needed in doing a project. Whenever you get a project, you form a work breakdown structure, which is a hierarchical breakdown of the work necessary to complete a project. A work breakdown structure elements should be identified by title, by a numbering system that performs the following functions. It identifies the level of the work breakdown structure element, identifies the higher level to which the work breakdown structure will be integrated, and shows the cost, that's the key thing, shows the cost account number of the element and how much cost, how many labor hours it's going to take to be. So that's a very, very important tool for in fact, when you go out and work in industry, you're actually, if you become a member of a work breakdown structure, you're graded on how well you perform under this work breakdown structure. That's the tool they grade you on. We'll put these charts on the internet. Role of the work breakdown structure: project and technical planning and scheduling, cost estimation and budget formulation, project status reporting, and plans such as specifications and drawings. Now, those that said to raise their hands, where did you find out, where did you learn to do work breakdown structure? Can anybody answer me? Where did you learn to do that? Those of you said you're familiar with it. Yes, sir.
I learned it here at MIT.
Did you? Very good. So they taught you how to perform, that's very good. And what course was it?
It's not a course, it's my research.
Well, your research. Did you find it hard to do?
I found it initially difficult to think about.
Yeah.
Once I realized how to work it, I definitely saw the benefits of that approach.
Very good. Well, it's an important tool that you need to do, and that's why it's a little hard to. That's why it's probably a little hard for you to do cost estimation, because you're not used to some of these things you need to do to get the cost done. Well, some of the basic elements of cost estimation is understand the product, develop a detailed work breakdown structure. Did you do that for this project? No. That's okay. I didn't mean to put you under the gun, but understand the development of the culture. Understand the culture. It turns out the NASA culture it turns out to be pretty high level because it does involve risk. And to give you a little story about it, somebody asked von Braun one time why NASA had to gold plate everything. He said because if you made out of pure gold, it would cost too much. So it's not that they gold plate everything, but it's that you really have a life concern in a very hostile environment. So you have to understand the development culture, gather data from close analogs, develop the cost estimating relationships. There are books, there are textbooks that show you how to develop CERs. There's a large society called Parametric Analysis, Cost Analysis, and in that you can get how to develop CERs. I'm not suggesting you necessarily do that because it is very, very time consuming, but just know that they do exist. There are, by the way, computer programs, very sophisticated computer programs, which I'm going to talk about, that develop the CERs for you based on inputs you give them. These programs are very expensive. One's called Price. I'll show what the other one is, and it's actually it was developed by RCA. It now is owned by the Martin Company, or was owned by the Martin Company. Group CRs according to the work breakdown structure, and you need to quantify the risk in the method, estimate the cost, spread the cost, and do a reality check. So those are some of the things you need to do. Now, in understanding the costing and analysis process, as I said, you need to understand the project, participate in the design team activities, scoping, inheritance, and complexity, identification of content, scheduling goals, collecting cost estimating inputs by weight statements, technical characteristics, preparing the estimates, CERs, translating labor hours and dollar hours. And this is a lot of details that you're not going to have time to do. But you do need to understand the complexity that doing cost analysis entails. It is very, very difficult, very hard to do. And you have groups set up to do it. But on the other hand, engineers working on a project are going to be called upon to do it, because you're the best source of information that they have to do it. Here is the basic building block of the parametric cost estimating is a relationship of the cost estimating relationship. And the dependent value variable is cost. The independent variable is something that you can understand. It's weight, power, ISP, and so forth. It's specific engineering terms. And you can relate, there's some relationship between weight, certainly for structures. There's certainly a value based on historical data points of weight of the structure, the type of materials, and so forth on the CER, the cost relationship. So that's how it's developed. My students had a very difficult time using this program because they didn't know how the CERs were developed. It frustrated them because here was this magic program that calculated the CERs for them. Right, Josh? Josh was one of my students. And they had a very difficult time trying to understand how to use the program because they couldn't understand how to do the CERs. But there is a methodology in it, and there are many books that explain it. The other thing that's important, as I pointed out, is the cultural variable. The cultural variable is this. This is one unit dry weight, and it can show the total cost, but it can show that for aircraft, you're on one cultural plane. On unmanned spacecraft, you're on another cultural plane. On manned spacecraft, you're on another cultural plane. And you're on planetary spacecraft, you're on another cultural plane. So that is a very big issue. One of the issues with NASA, they say to get the cost down for NASA, you need to change the cultural plane. Of course, if you change the cultural plane, you probably have to give up something. You probably give up some risk in terms of safety or margin. So you got to recognize that the cultural variable is a very strong indicator of, are you happy to note that the aircraft is so low and everybody flies on an airplane? But that's the cultural variable that it shows, that for structure, you can see how the structure varies based on the cultural plane of cost plan.
And it's interesting that, when you were talking about like using square footage as a rough estimate for a house, and we do in the space business, we do use weight as kind of a substitute for cost. You can translate from weight into cost, and yet people always point out, well, yeah, but a kilogram of aluminum structure costs a lot less than a kilogram of computer chips. But nevertheless, when you put everything down, when you're designing a planetary spacecraft, they do have these estimated relationships. Yeah, if you're gonna have a project which lands 150 kilograms on Mars, compared to a ton on Mars, we do have these relationships, because in general we figure that the ratio of hardware and software and computer chips to aluminum and all that is roughly similar. But if you're going to try to build something that's fundamentally new, which involves a lot of new technology, then of course you can go way off of these rough estimates.
To get a good understanding, you might say a very quick understanding, you might go to the NASA website and get parametric cost analysis. It will give you a very good understanding of what you can get. And you can get some of these programs off the internet today. They're not very sophisticated, but they do have some CER relationships, as Jeff was talking about. It might be a little bit more difficult for some of the items. Unfortunately, structures would be an easy item to do, but I don't think anybody's doing that. But it would even be good for the avionics system, I think, in life support, yes.
Are these software packages basically just a large database?
They're basically a large database that you put in the data. You can put in in fact, they're so sophisticated now, you can put in the software, the type of software you're using, the number of lines of code, and it can tell you how much it's going to, and based on the CER for that particular subject, it can tell you how much it's going to cost per line of code. They're very, very sophisticated, and most companies use it. NASA uses it quite a bit, yes.
But this
software you must have to upgrade it or update it very,
They update it very frequently.
to cope with technology changes.
That's right. They do update it quite, and that's why they're so expensive. They're very expensive, but they update them. They've got, for example, when I started using it at A&M, and they didn't have even a software package in there for composites. Now they have one for composites.
And there are a lot of these which are proprietary and you
That's
can't
right.
even get access to. I mean, the Aerospace Corporation has compiled a huge database of costs of a lot of components, historical, and to how much it was estimated, how much it actually cost. And so NASA and the DoD often go to aerospace to do cost analyses for them. And of course, aerospace charges, and they don't release their database because it's proprietary, so that knowledge is power and money in this situation. They put a lot of work into putting the database together.
Yes.
In fact, I have seen one of these software in the NASA website concerning space launchers for LEO orbits.
Okay, were you able to try to use it, or did you try to check it out?
I didn't try. I had no time, but anyone could use it.
Yeah, and some of them are very, but of course it may not have the update as this gentleman was talking about, but it has a certain amount. So you could do a pretty quick analysis. Yeah, I would suggest you try to do that. I would suggest you try to do it, because I know that I had looked at it, and there are ways to do it. Now you got to be careful of the results, because sometimes the results become pretty high, but you got to be careful of the results and look at it pretty carefully. This is another development of cost scaling law. This is happens to be weight versus, you can see that the two different cultural planes, known cost and weight, unknown cost from a given weight. So this is basically how they generate the CERs. It's a process. It is an analytical process, but there also is a lot of empirical data that goes with it. And as Jeff said, they have it's based on a large database. Now, cost estimation. Now, I'm telling you how hard it is to do, and you probably already know it. But for a cost estimation, you need. Now, this is after you get over the era of parametric cost analysis. Now we're talking about how you do a cost analysis when you're really trying to figure out how you go forward to ask for a budget. You need a fairly detailed design information. Unrealistic for designers to give cost information for conceptual designs, but designers must be able to make rough cost estimates. So that's what I'm saying, that you do need to be able to make rough cost estimates. Now, if you're trying to make a detailed cost estimate, what you really need, and that goes back to the work breakdown structure, you need the number of labor hours and number of people on the project. I mean, people is probably going to be your most expensive project. So you need the number of labor hours, number of people on the project. During the shuttle program, I was a project manager. I used to call my counterpart at Rockwell every Saturday morning, and we would go through how many people we had on each work breakdown structure for each contractor. We would talk about it to be sure we had the budget to cover it, and then of course we had to be sure we got the product out the door. But the number of labor hours, number of people on the project, the length of time these people are going to be on it, the overhead rates, office space, computer, benefits, cost per hour of a person, basically, is what you're looking for. That's how you really do a cost estimate, and finding out. And of course, it's going to vary depending on the locale of the contractor. What are the cost drivers? Now, here's where the cost comes out. Some of the things that Dr. Hoffman was talking about. The errors in the design, change in requirements, poor interface definition, technology development, poor communication, poor teamwork. This is all elements of systems engineering that have gone awry, that have not gone in the right direction. But those are what caused the cost to go. In my experience, the biggest problem in cost estimates have been the changes in requirements. That's really the thing that's caused most of the problems. That's why you need an early good definition requirements and not change it. Technology development, that can cost you a lot of money, but sometimes you have to go forward with it. Now, this is old data, but This is 1993 data, but I got this from a contractor a long time ago. First of all, what you need to do, and of course it's a lot different. I don't know if it's higher or lower today with CAD systems. This was before they really used CAD systems. But this is the average cost of an engineering drawing. And it goes through how you do it. It's probably the labor rates are higher today. The average hours per drawing are probably lower. But this says in 1993, the rate is an estimate for 1993 government year of about $3,000 an average drawing. So you have to figure out how many drawings you need. I mean, that's a good way to understand the cost estimate of what's going to be. So you need to know how many drawings you need, and you need to make a cost understanding the cost element. The elements of cost during manufacturing then are the number and complexity of the drawings, cost of a drawing, number and complexity of machined and fabricated parts and what the parts are made out of. Aluminum, steel, titanium, nickel, Inconel, and so forth. Because each one is a little bit more complicated some are more complicated to machine than others. But some are used in the space program, some are not. Titanium is becoming more and more important. And other things in manufacturing are tolerance of parts. Turns out engineers tend to you might say, put extra tolerances on parts that they don't need. And that can cause parts to be very, very expensive. The finish of parts, the quality of parts, assembly and complexity and time qualification, check-out test. I remember my first day at work when I worked for RCA. I was designing a tube, a microwave tube, magnetron. So I sent this, I was a terrible draftsman, as a matter of fact. That was a long time ago. I'll probably be better with CAD systems, but I sent out this part to the shop, and this guy coming in, chewing this stogie. He was out in the machine shop, and at that time we sat in these big bullpens, each person at a desk, and I had my name on my desk. And he comes in this big room and says, "Where the hell is Cohen?" That's me. He said, "This is the dumbest drawing I've ever seen in my life." So how do you expect anybody to make this part? He said, "The tolerances are..." So you got to be sure you understand what you're doing. And it turns out I learned to work with that guy, and we became good friends. That never happened again. But he wanted to know where the hell was this guy Cohen who put out this dumb drawing. He said, "There's no way I can make this part." But so you need to understand, and that was a small part, but you need to understand the complexity and of the part and what you're putting out to the shop. But today they have checks and balances, and with the CAD systems, I'm not even sure this is accurate anymore. This about brings me to the close of what I wanted to talk to you about, but let me just give you one final chart, and then I'd like you to ask some questions about anything I covered or anything anybody else covered, because we're going to that you heard about. I would stress that for you today in your course is to try to use parametric cost analysis. That's what I would think you should do. At least that's what I think you ought to do. And I think you can get information off the internet that will allow you to do something. Now, it may not pertain to all projects. I'm not saying you have to do it, but it might be the thing to do. It's going to be very difficult if you did the right thing by creating a work breakdown structure and trying to do that. It's going to be very difficult for you to do it in this course. But parametric approach to hardware costs are not produced from parts lists and labor tables, so you don't need that. Produced from general measures of the impact of such items' cost, and in preparing inexpensive and more realistic and manageable cost estimate based on cost estimating relationships. You might want to do some reading on cost estimating relationships, and there's a lot of references to that, just to be sure you understand what I'm talking about and what they are, so it's not a mystery, a complete mystery to you, so you get a better feel for what it is. A lot of textbooks have it, cost estimating relationships. CERs make use of characteristics that can be readily quantifiable, such as weight, size, and to estimate variables that are difficult to quantify, such as cost and production schedules. As I said, parametric models can range from a simple arithmetical relationship to a sophisticated computerized model. So they can be very, very complicated or very simple. And I suggest you try to do that. Let me just show you what the programs are. Not that you'll be able to get them, but when you get out in industry, if I can find them here, well, I may not have them. There's certainly a lot of information on the. here's the price model. That's price H, and you can actually do structural, weight, material types, tolerances. You can actually do electronics, digital, analog, technology. So you do have quite a bit of latitude of what you do. Now, you're probably not going to get that program here because it's pretty expensive and pretty hard to do. But when you go out in industry, our government, there's a very high probability you'll be using some of these programs. And there's another one that this is used. Johnson Space Center uses this one, and the Marshall Space Flight Center uses this one, CIR-H. So there are two programs that are used by NASA, I know, and they are becoming more and more important as we go ahead.
Aaron, one thing you haven't discussed in all this discussion of cost is margin. And you know, as a manager, you have to deal with that. So maybe you can make a few comments on that.
Well, let me start off this way. What Professor Hoffman's alluding to is that when you create a budget, you want to have some type of reserve or margin over and above your cost estimate. And that takes care of several things. It takes care of changes, it takes care of I forgots, and it takes care of inefficiencies. They have found, work has found, studies have found that in a high technology program for the first time, you're about 30% inefficient. So you're only about 70% efficient. Now, this was data taken some time ago. You're 70% efficient. So you need to allow some type of margin in that for your inefficiencies. But if you do that, and then you talk about changes, and you talk about I forgots, your reserve becomes very high. Normally your boss, the guy that's over you, is not going to let you have that much money. I know when one of the investigations we had on me during the shuttle program, because my cost was growing, a very famous man came in to be head of the program named General Abramson. Many of you may have heard of General Abramson. And while he was he did the investigation. He said, "Aaron, you need a large reserve." So when he became manager of the he didn't know he was going to become manager of the program. So when he became manager of the program, I had this large reserve in there. And he was reviewing me. He says, "You can't have that much reserve." so he whacked it down. But you do need a reserve, because you're not going to make it without a reserve. And if you noticed I don't know if you noticed or not, but in the papers I gave you on the cost of the shuttle systems, it had about a 30% reserve in there. When I did the study for the 90-day study, I had a 50% reserve in there, because I felt that was a pretty far out program. You needed a reserve. But a reserve can, you need to fight for your reserve, but I guarantee you're not going to get everything you think you need. Yes, sir?
Every time, for something like aerospace, every time you do a cost estimate, the top guy will look at it and say, well, let's increase that by 50% or double it. And often, even once you've done that, you still don't come under budget. I mean, look at the ISS or the Airbus 380, that's blowing out. Why?
Well, again, it's because it's really because of first of all, it's primarily for the inefficiencies. You just cannot do a high-tech program. Look what it costs to do the Big Dig. I mean, to drive it home. Look what it costs. It's very difficult to do a good cost estimate. But that is the problem that Congress sees with government programs today, both the Department of Defense and NASA, that they can't do a good cost estimate. The current program says they're going to do the CEV and go to the moon for $104 billion, which is 55% of what it costs to do the Apollo program in current year dollars. And that's going to be interesting to see if they can do it. It's tough to do. But really, I think the biggest problem is your inefficiencies. Of course, there are changes and I forgot. It does turn out, interestingly enough, you may or may not believe this, and you probably won't, but I'll say it anyways. It turns out that the studies done for the shuttle program, for the Arbiter, actually, in real year dollars, met the cost of, if we would have gotten the inflation rate. We lost the inflation for 2 years, which Dale Myers fought for vigorously with OMB, and we lost the inflation for 2 years. If it had gotten the inflation for those 2 years, we would have come in cost for the development cost, not for the operational cost, but for the development cost, we'd have come pretty close to it. So we didn't really miss it that far. In Apollo, the story goes, I'm not sure, but you need to ask Dr. Siemens. The story goes is that NASA came in with an estimate, and that time the Administrator Webb looked at it and said, that's fine, and he doubled it. And so the Apollo did very well.
The story we heard, I think Bob Siemens has told that.
Bob Siemens.
It was on their way over to the White House.
Yeah,
he said, you know, our final estimate, you know, and we've put all the factors and everything in, is $10 billion, and Webb said, okay, we'll tell the president 20.
Yeah, well, I'm sure Bob Seaman would know.
Yeah.
Yes.
Aaron, I want to ask you about the location of the reserves, and not just dollar reserves, but my experience as a payload user.
Yeah.
There's reserves of weight, there's reserves of crew time, there's reserves of electric power, and so on. The model I've been faced with is that the mission manager has a reserve for crew time or for weight or something. But you know, down at the project level, you would really like to go and have your own. And so there was a tendency for everybody from the lowest level, from the individual experiment up, to say, well, I'm going to put in a little bit of pad rather than count on the fact that I can go up to the mission manager and ask him for some reserve later.
Well, that's the danger with that. You're absolutely right. Everybody would like to put their own reserve in. Of course, being a project manager, I thought the reserve ought to be at my level. But actually, John Yardley was my boss in Washington, and John Yardley thought he should handle the reserve. And so basically, he would take my
subsystems managers their reserve.
Right. Their reserve.
Right.
So so basically, John Yardley was another person I should have mentioned. John actually basically pulled the reserve up and handled it in Washington. So I had to go back.
There's a certain efficiency, I assume, in having all the reserves centralized, so that there's not a lot of wasted down at the lower levels, but you have to have the confidence that you can be able to draw.
Right, and with that, John would partial out some. What he would do, he would be sure that you weren't double reserving him or triple reserving him, and then he would allocate it to me. I know he had a rule of thumb. When J.R. Thompson went up, you heard J.R. talk. When J.R. Thompson went up, he always asked for more than he needed. So John would give him less. When I went up, I always asked for less than I needed, so he would give me more. So he had a good feel for his managers, and that's what he told J.R. one day. But normally you wind up handling it, if you have a good program manager at the top, you normally wind up handling it there, and he parcels it out based on the fact there is no double bookkeeping. Yes, Jim?
My experience at Draper is typically, there are two different ways of estimating. One was called top-down, the other was bottoms-up.
Yeah.
And traditionally, bottoms-up would always stick their reserve in some way. And top-down would always say, I want to know what your reserves are because I want to bring it up to the top.
Yeah.
And that was a constant argument. Then when you got to submitting your proposal, often the customer didn't want to know about this extra money.
That's
You'd
right.
have to shove it back in and hide it, in a sense, by padding things.
Yeah.
So handling costing and reserves is to some extent, at least in my experience, has been a psychological thing, dealing with customers and your management. And it's always been one where you shuffle that reserve around.
Well, but this gentleman asked a question about why does it appears that NASA never can stay on their budget, and that's really a tough question to answer. I don't know. I mean, I have no personal feeling on it, but it's. I think the basic problem you have is that it's a high technology program. It's one of a kind, and it's a lot of inefficiencies. When you come to work every day, you don't know exactly what you're going to do. You have a technology development that causes, you have I forgots, you have changing requirements. Changing requirements are something that systems engineering ought to be able to control. I forgots are something systems engineering ought to be able to control. Inefficiencies, to a certain extent, systems engineering ought to be able to control. So that's one of the purposes, in all honesty, that's one of the purposes that are concentrating on systems engineering, on such places at MIT and other schools, to allow the future generation of designers and developers and working, that they can have a budget and then stay on the budget. So maybe in your generation, you'll be smarter and able to control it. But it's not going to be an easy job. But that's one thing I would say.
Let me just make one other comment on. We can't estimate too much that you've got to always keep in mind this triangle of cost, performance, schedule. If you're working on a project where the schedule is fixed, like Apollo, then that better ring the bells to say that I need more reserves. And, maybe that's what was going on in Jim Webb's mind when he said, if we really have to get this done by the end of the decade, I better make sure that cost is not going to, that I'm not going to be constrained there, and so I'll double it. The other thing that you have to take into account with the performance is how much new technology is this program going to require? Because the new technology that's the hardest thing to estimate the cost.
That's right.
And so you better, if you have a new technology program, then your margins better be big enough to accommodate that. That's why for the CEV, they're really going out of their way to saying, to the maximum extent possible, we don't want to develop new technology for the CEV. We want to use shuttle parts wherever we can, Apollo heritage. We want to build it out of things that we know and we understand, so that we, hopefully can keep the cost as low as possible. And we'll see how it all works out.
Yes, sir.
It seems to me that you oftentimes have the pressure to give the cost estimate on the low end of what you believe it to actually be, just so the project might be more appealing.
That's certainly another part of the whole political thing. And not just from the political point of view of presenting your estimate, when NASA presents the estimate to Congress, but then you have the contractors who want to get the contract from NASA. And you've certainly had experience with this. How do you deal with the contractor who lowballs and then assumes that they'll be able to make it up later on?
Lowballing is really should not be tolerated, and they try to do that, not tolerate. But you're absolutely right. When I did this 90-day study, I really felt they wanted to know what it was going to cost. So I had a 55% reserve in there because I really felt that there were so many unknowns with it, and of course that didn't go over very well. They said my study actually killed the projects, but I told them what it was going to cost. So, see, Larry. Thank you.
And then, this is a subject for another lecture entirely, which I'm not sure that we're going to do in this course, but there are many different ways to let out contracts, fixed price contracts, cost plus contracts, award contracts, and all of those can have an impact on the ultimate cost of your project, and they all have their utility depending on how well the technology is known and what is the time pressure. Again, cost, performance, schedule. And if you, you asked about Airbus, and I don't know the specifics of Airbus contracting, but I am familiar with ESA, and because of some of the peculiarities of the European system, they tend to use fixed price contracts a lot more than we do here, and sometimes it works, but sometimes you get really burned on it, because contractors are not going to go into bankruptcy because they can't deliver on their fixed price contracts.
You try to go fixed price on the CEV and it would cost you a fortune.
Yeah.
I mean, those are very good questions. Unfortunately, we don't give you very firm answers on cost, but at least you're thinking, and I appreciate your thought process. It's very encouraging to hear you ask those type of questions.
Have a good weekend.
Yeah.
We'll see you on Tuesday.
Yeah.